Hello everyone. Today we are going to talk about interrupts. Before we start, what do you know about interrupt? Or let's take the English word interrupt or interrupting. So it's actually, let's say you are doing some work, someone comes in and asks you to do something else. So as you are doing work and someone asks you to do something else, then apart from your own work, this is actually someone is interrupting your own work. So for example, in a class, we are doing a lecture and someone comes in and asks us to leave the hall because of the fire. Or we have to go to the labs from the lecture and do something else because that's more important now. So what I'm trying to highlight over here, interrupts are some kind of events or the exceptional events, let's say, that it's changing our normal conditions or the normal progress. So what we do, we actually hold that the normal progress somewhere or save it somewhere or leave it there, do the other task which is interrupted as, and then we can go back and return to our normal progress or the flow of the event that we are having. So this is what interrupt is. And when it comes to AVR or the embedded systems, interrupt is playing an important role in a way that we can actually use both the internal and the external resources, like the hardware resources, and we can generate interrupts and we can create the routines that when the normal program runs, we can have these exceptional routines, and apart from it mainly running in an original program, we can go to this routine and do something else. So these are exceptional events that we are going to see. This is how we can define an interrupt. Then what we are going to see is how are we going to use these interrupts. So the registers defined in AVR, the interrupt unit, which is a special unit in AVR, and the vector tables and the different types of hardware that are generating interrupts. How are we going to set those up? We are going to see those, especially the timers and the priority of the interrupts, so we can have a different interrupts coming to our CPU, how it is going to be prioritized, and maybe interrupt inside an interrupt. So one of them is running the interrupt, so another one comes in. So what are we going to do, and so on. And also we have to take care of the stack and the registers and all kind of resources that are we using during the execution of an ordinary normal programs. So this is the outline that we are going to follow in this lecture, and interrupts is actually quite interesting, and they are really quite useful. So before we go into the details of it, let's see the definition on the slides as well. So interrupt is an exception, as we already said, a change of the normal progression or interruption in the normal flow of the program. So you can interrupt you can interrupt the CPU. It's the same idea or the same manner, let's say. So we are going to see this in detail, and as we already said, they are just the hardware generated function calls. It can be internal or external. So interrupts are causing us to hold whatever we are doing, the normal flow, and perform that interrupt routine, which is generally executed in the interrupt service routine. We are going to use this a lot, ISR. And once we are done with the ISR, we return back to the normal execution and we carry on whatever we were doing. So we can give different examples to this. For example, the computer is running, I just push a button and reset the computer. Or maybe I'm receiving something from outside. Maybe analog to digital conversion, or the timer ticks, so when it reaches to some amount of time, do something. So these can be an events of interrupting the original flow of the program. So how does AVR is handling this? This is another important measure over here. AVR takes 4 cycles maximum to respond to an interrupt. It's quite fast, 4 cycles. Because what it does is, it saves the original routine's program counter on the stack, then jumps to that interrupt vector to serve the ISR, the service routine, and then when it serves the service routine, it clears the flags and get back from the stack the program counter position, and then return back. These are all happening in 4 cycles. So it's quite important over here. So if response time is critical, really critical, we can use a tide or a polling loop, which can help us in a way that it's the cycle wise it can be faster. But on the other side, with the polling, we have to hold, we have to wait. So now let's see the difference between polling versus interrupt. Now you might say we haven't seen polling. We actually seen polling. Where we have seen it, I don't know if you do remember from AVR timers, we had a routine or the instruction, if you do remember, SPRS R20 TOB 0. So this routine is actually checking the timer zero overflow flag, and if it's not set, it returns back and keeps waiting over there. So what it's actually doing, it's doing a polling. So the polling, the CPU, it does not perform any other operation. It is just waiting for event to occur to do something else. So let's imagine this in another way. Let's say you're planning to go out with your friend. You go to your friend's house, you wait there until he or she gets ready, and then you go out. But while you're waiting there, you're actually wasting your time over there. You might do something else at that time. So that's what is happening with the polling in CPU as well. Okay, you go over there, you wait for an event to occur, you wait for the flag to occur, then when it occurs, you perform a subroutine or something else as an instruction, then return back and wait again. So polling is actually using round robin fashion. So it has to go each resources and wait for it to event to occur. It checks everything one by one. And in polling, the microcontroller continuously monitors the status of a given device, and when the status condition is met, it performs the service. After that, it moves on to monitor the next device until each one is serviced. So we are actually wasting quite a lot of CPU power over there, and it's just a wasting of time. So that's why polling is not really useful in embedded systems environment. On the other hand, interrupts, you can use interrupts, and in that case you can perform something else, and whenever the conditions are met for interrupt event to occur on the internal or external hardware, you just stop whatever you are doing and serve that interrupt first. And if you think about as a coding wise, polled code is generally messy. You have to create the branches and check again and again for different devices. But with the interrupts, you can just use the interrupt service routine, which can handle everything in a tidy place. So you just need to mention which interrupt service you want to use, the timer or external or a, let's say, ADC. You just specify that one and the AVR deals with it. On the other hand, the polled code lets to variable latency. So again, the time taken to serve the branches, if not branches not taken, wait over there. But with the interrupts, you can just have highly predictable servicing latencies. So we are going to see this in details, and I think the next slide over here is just showing another polling versus interrupt. So polling, in summary, ties down the CPU. It's not preferable. Interrupts, efficient. CPU can do whatever they want in an ordinary fashion, and whenever the interrupt comes in, it serves that. It has the priority based on the interrupt vector table, which we are going to see. It can be masked. So do your common task. Whenever the interrupt comes in, do that routine. So this is what interrupt is and how it is compared against the polling. And there are more definitions over here. Interrupts are serviced in microcontrollers or microprocessors using the following procedure. So what is happening with the interrupt service routine is, I think it's pretty straightforward. So for each interrupt, there is actually interrupt service routine. There is a unit in CPU which is dealing with these interrupts. There's a special service over there, or we can say them interrupt handler. So whenever an interrupt is occurring, the microcontroller interrupt service routine deals with it. So how it does deals with it? So in every microcontroller or in a microprocessor, there's a fixed location in memory that holds the address of that service routine. So if it's for timer, there's a special place in the memory for that timer. If it's an external event or the hardware, there's a fixed place in the memory for that. So ISR, the interrupt service routine, it holds those locations and set aside for the whenever the routine comes in, it goes through that one. We are going to see those interrupt vector table later on. So now, when we have got the interrupt, what it does, it finishes if, for example, it's just outputting something on LEDs in ordinary program. Let's say we are just running and sending out some values on LEDs. Whenever the interrupt comes in, okay, we finished outputting those values on LEDs. We save the address of the program counter for the next instruction onto the stack. So be careful, we have to use stack. And then we check, the ISR checks where is actually this interrupt is going to be held. So from the interrupt vector table, it jumps to a fixed location and find out that service routine that we need to run. And then we jump into that service routine and start to execute that routine. So in that routine, it's like a subroutine. We are just going through an instructions, which we are going to see in a minute. And when you come to the end of those, for the ISR, we have got a special function, which we call it red eye. Red eye is actually telling us, go back to stack, get whatever we have got as a for the program counter for ordinary program that we are having. Go and take that one from the stack, put it back into the program counter and jump to that instruction. So you might ask, what's the difference between red eye and red, which we are going to see in a minute. But red eye, that's also returning back from a routine, that also returning back from a routine. Both of them are returning back from the routine. That eye is actually clearing the interrupt flag. So that eye clears the interrupt. That means we are ready to wait for we are ready to get a new interrupt from another resource or from the same resource. That's why we use red eye. So that is what is happening. Another important thing during the ISR, so when ISR is executed, the first part of ISR typically saves the context. It's known as context saving. So what it actually does, if we are using same registers in the main program or in the interrupt, we have to save the status of that register or the value of that register to somewhere, so there won't be any problem there. We don't update that during the interrupt, because we are going to, if we are using the same register. So we save that onto stack, which we call it context saving. We save that on the stack, we perform the routine if we are using the same register, and then once we are done with the routine, we pop out from the stack that value that we have got for that register and carry on with the ordinary flow. And then again with the red eye we go back to the ordinary form. So CPU then resumes executing the original instruction stream. So these are the steps that we generally focus on interrupt servicing. You have to know the idea of how the CPU or the microcontroller serves an interrupt. So next thing that we are going to talk about, reentrant subroutines. So what is reentrant subroutine? So when real-time control software uses interrupts, a given subroutine can be called before it returns from a previous call. So the subroutines that we have created in our program, they can be used both for the interrupt service routine or can be something else. So for example, you want to call a delay subroutine, delay 1 millisecond or a microsecond. This can be also called in the interrupt service routine. So they have to be reentrant. So how do we make a subroutine reentrant? We just need to specify a simple parameter passing with an obsolete memory addresses, and this can be done with the stacking again. So what is important over here, we have to be careful that we don't actually updating the same parameters on different subroutines at the same time. So this is important. So if you write programs with reentrant subroutines like factorial or Fibonacci's, you will want to think about utilizing the stack to save the context when needed. Otherwise, you can execute the same functions at the same registers at the same time, and this will cause an error. It might have a stack overflow as well. Okay, so next thing is the reset. So reset on a computers, reset on the microprocessors, or reset on the microcontrollers. They're all serving the same idea. It resets the hardware, it resets the registers, the program counter, and the CPU states. So reset subroutine perform the initialization of the system. Whenever your system stacks or holds somewhere, you just press the reset button, which is an external interrupt, whatever it's running inside of it, and it serves that one and it initializes the system again. So reset is often used by the programs and the users to get out of an infinite loop. We have a different types of resets in AVR. Power on reset, which we already seen it. So if the supply voltage falls below the power on reset threshold, it has to reset to get a stabilized voltage over there. External reset, like we have said, we can push the button, reset it for a short amount of time, so it will reset all the registers and everything. Watchdog reset is related with the watchdog timer. Whenever it expires, it resets everything. Brownout reset, which we already seen in the previous chapters, that if the supply voltage again is below the VCC, it holds a brownout reset, and then brownout detector is enabled in this case, and it validates the voltage levels on the CPU before it's damaging the CPU. And we also have the JTAG programmer reset, so you can just reset the programmer, so scan chain is resetted and you are ready for the new transfer of data. Now, so we should now understand the idea of interrupts or interrupting a CPU and the difference between polling and interrupt. Now we are going to go into the details of the hardware side of the interrupt. But before we move on, I just want to emphasize something. This is something that we have realized during the labs and also during the examples that we are doing. So when we talk about embedded system engineering or embedded system coding, one of the most important thing is not about writing a code, okay? Because we are not actually doing exactly a software engineering over here. What we are doing is, with the embedded system engineering, we are actually defining what resources are required, okay? How are we going to use those resources? How are we going to set or modify the resources that we have got inside of the microcontroller to serve our needs? This is what embedded system coding or engineering is. It's not actually a software engineering. So we have to know exactly which registers are we going to use and how are we going to set those registers. The art of embedded system coding is over there. How are we going to use registers and which registers we are going to use, or which pins or which resources inside of a microcontroller. So from now on, I'm going to concentrate on these when we are writing a code or giving an example or defining the hardware resources that we need to use. So let's start with interrupt unit and global enable. Now, inside of our AVR, we have got interrupt unit. This interrupt unit is actually a number of interrupt registers which is related with the hardware resources that we have got over there. For example, timer, extended timer, external interrupt flags, the control registers related with it, and so on. On the other hand, apart from the interrupt unit, we have got two important registers in CPU, which is the MCU control register and of course the status registers. So SREG, which we have seen it in the previous chapters with the arithmetic operations and so on, we have seen most of these flags which are already set. So the most significant bit, which is digit 7 or bit 7 over here, it's actually serving the interrupt. So this is global interrupt enable. We can set this bit. Whenever we have set this bit, that means we are telling our CPU that we are expecting some interrupts, either from external or internal. But if we don't set this bit, even inside of our interrupt registers, we set and enable the interrupts. As this is not set, CPU is not going to deal with any of these interrupts. So whenever we want to write a routine which is related with the interrupts, we have to enable SREG bit 7, which is known as global enable for interrupts. Okay? So that means if this bit is 0, no interrupt can be generated. It is cleared when an interrupt occurs and is re-enabled when we do red eye, which we already mentioned over here. So again, I'm just going to repeat myself. The registers that are defining the interrupts for different resources of the hardware, internally or externally, even they are set it for interrupt. As this is not set, the CPU is not going to serve any interrupt. If you want CPU to serve an interrupt, you have to set the global interrupt enable bit, which is in SREG bit 7. So let's see the details of these registers now. So one of the most important interrupt function or the routine is coming from external events. So external hardware, a sensor, can interrupt the CPU, or something else can interrupt the CPU, which is important in these cases if you are dealing with the outside world. So we have got two registers over there: external interrupt mask register, so in0 to in7, and we also have external interrupt flag register. So we have got special pins over here which are dealing with the external interrupts. In 0 to 3 over here, in 4 to in 7 over here. So port E and port D can be used for external events. So we can configure port E and port D for external events to be occurring. So we have to set these flags if an event is occurring, so interrupt event is occurring, and we can deal with EAMSK, external interrupt mask register. Then we also have external interrupt control registers, EICRA and EICRB, which is the sense control bits we have in those, determines if it's going to be a rising or falling edge or low level triggered, and we can set these up from ISN 1 to ISN 0 over these bits, and we can figure out if it's going to be any of these settings that we are detecting an interrupt from. So interrupt control registers, for example, for the timers, we are using timer interrupt mask registers, which we have got the timer 0 overflow interrupt enable, output compare 0 interrupt enable, timer 1 overflow interrupt enable, output compare 1B interrupt enable A, and timer 2 overflow and timer 2 output compare. So these are all interrupt bits that we can use for the timer, or you can have the extended one for 3A, 3Bs and so on, or 3C. So we are going to see a couple of examples related with these and how we are setting these things up. And inside of the CPU, we have got the microcontroller control register, and the interrupt vectors are these two bits, the last two bits, bit 0 and bit 1, IV cell and IVCE. So IV cell is interrupt vector select to place the interrupt vectors, which we are going to see in a minute. It can be placed into the beginning of the flash, which we generally do it, or maybe boot flash section 1. So with IV cell, that's how we are setting based on ones and zeros. And IVCE, it's actually, we have to set this one because we want to change where we are putting the vectors. We have to enable that one first to activate IV cell. Okay? So without that one, this cannot work. Now, so we have mentioned everything that we need, the registers that we are going to use, with the including the CPU registers and the ISR or interrupt unit registers that we are going to use. But the most important thing is the interrupt service routine, or the vector table for the interrupts. So don't worry, you don't need to memorize any of these. This is given in the datasheet I will provide you all the time, and if you are doing a work by yourself, you can check this out from the datasheet. So interrupt vector table shows us what kind of interrupts our AVR can handle, and these are coming with their own program addresses for the ROM. So as you can see, 0000, it's actually reset interrupt. It can be external, power on, brownout, or whatever it is. So address 00 can be used for interrupts. So what is important over here? all our interrupt vector table can start from the program memory 00 and goes up to 0044. So over here, if you want to use interrupts in your programs, you have to allocate that space for interrupt vector table. That means you should not initialize your main program to start from 0. So normally what we were doing .org, and we start doing some operations underneath because we are starting from program memory 0000. But if you are going to use interrupts, this shouldn't be the case. You should start somewhere after this interrupt vector table. So what we generally do, what we say is, let's say .org 0. Okay, with .org 0, we are specifying that the program counter 0 location, it's going to have the first instruction as, let's say, jump main. And what we are doing, somewhere here, we define another org, let's say, address 100, and then we start writing our main program over here. So we don't put any instructions in from 0 to 100 because we are saving that location for our vectors. And also note that the instructions or the interrupt vector tables are also 2 words or 4 bytes of ROM space are assigned for them. So for example, 0000 and goes up to 0001 is for reset, but 0002 to 004 it's interrupt 0. So 004 to 006 is interrupt 1, and 006 to 008 is 3, and so on. So each of them has their own 2 bytes or 4 bytes of program memory location assigned for them. So this is also important metric that we need to take care. So what we can actually do with the vector table, you can use boot reset fuse. When it sets it to 0, then the interrupt vector starts at a different location. Depending on your configuration, you can put in a different part of the memory. But generally, what we do, we start from 000. So in most of our examples, we are going to use these addresses which is provided by the datasheet. So we are going to stick with the original codes. Okay. Now, what we are going to see is how interrupts are executed in AVR. Again, we have got a short program over here. On the left, we have got the AVR pinouts, and of course, one of the important thing is the stack. So over here, as you can see, on int 0, which is an external interrupt 0, we have got a connection over there, which we are expecting some external interrupts to be happening. Now, let's go into the details of this subroutine and see how it is going, the routine, not the subroutine, how it's all work together with the ISR, interrupt service routine, and so on. Now, if we start, so as you can see at the beginning, okay, we have got the definition file. .org location for reset. So then we have got jump main. So we are actually saying that we are going to allocate this space for interrupt vector table. Then this means we are going to jump directly down. So over here, the program counter is 4. That means when we reach there, we are going to jump as the next instruction to main and start with LDI. So when we reach there, the program counter increments and start to allocate, as you can see, the RAM end, the end of the RAM memory for the stack. So this is actually going through the instructions, and we are allocating the memory for the stack. And now our stack pointer is set it, and we are ready to carry on. And instruction 8 is shown. The next instruction is setting bit on C port to be an output, and then on port D, so bit 0 pull up is activated. Then over here on the next instruction, which is 0A, we are actually setting enable interrupt 0, because as we are using interrupt 0 on here, you can zoom in and find out that this is int 0. We have to set this pin that we are expecting an interrupt over there. To set that, we have to go to external interrupt mask register. So in external interrupt mask register, we have got int 0 bit. So in 0 bit, it has to be set 1. We can just do that with a GPR register R20, and then on the next instruction, we can just set this value to be 1. Then SEI. So this is which we already set in the status register. We have got the bit 7, which is the global enable. So as we are enabling external interrupt from the interrupt unit, we also need to enable the global interrupt. So by just using SEI for enabling set interrupt enable, or for clearing it, we can just use CLI, which is clear interrupt enable. So we set the interrupts and we are ready to carry on our work, but whenever the interrupt occurs, we can just jump to the service routine. So SEI is done, then we just do a normal LDI operation, so 3 and 4, and we keep adding those stuff. So while we are adding those stuff, external event starts to occur. So that is actually pulled down to 0. That means something is coming in. So we have an incoming event. That means the next instruction, which is 00F, is going to be saved onto the stack, because we have to jump to the interrupt service routine, and when we finish the interrupt service routine, we have to go back to our main program and carry on with this instruction. So 0F is the low byte of the stack, and 00 is the high byte of the stack, and those are saved. So low byte of the program counter, then the high byte of the program counter are saved on the stack with the stack pointer. Now, as we have saved the program counter locations, what we do, as this external interrupt routine is going to be called from vector table 02. You can check the vector table 02, because this external ISR is happening over there. So we have to specify the location 02. Okay, so .org02 has to be specified that we are waiting for external event from the vector table. We have to specify that. Then the program counter jumps back to 2, as that is stated with the interrupt service routine. So we come over here, and the instruction says jump external 0 ISR. External 0 ISR is the routine for the interrupt service. So that means from 02 we are going to jump, as the next instruction which is placed in the program counter is 12. So we jump down to the interrupt service routine, and over here we are getting a value from port C stored in R21. Then we have got the number 8 stored in R22. Then we do an XOR and output on port C. So we are just flashing some LEDs over there as an external interrupt service routine. So we go through each of these instructions. Over here, what is happening is interrupt service routine is actually setting. In other way, it's clearing the flag for the interrupt because it's currently serving an interrupt. So you cannot have interrupt serving another at the same time that you are serving one. You can do that, but in this case, it's not the case. We are going to see that as well. So once the interrupt is done, red eye instruction returns back to the stack and also clears the interrupt enable. I mean, it sets the interrupt enable and it's ready for the next interrupt event. Okay, so in this case, it goes back to the stack, get the value 000F, put that into the program counter, and jump back to there. And we just carry on of what we are doing. We just wait there by added of R30 and R31. And that's it. So this is actually showing how AVR is executing an interrupt. If you have any questions or if you have any difficulties of understanding this, note it down and then we can discuss during the question and answer session. So once again, the steps that are necessary to enable an interrupt, we have to define which interrupt register or which interrupt, let's say the resource is going to be used, external or internal hardware. So based on that, we have to set the register inside of the interrupt unit, and we have to enable the global interrupt from SREG bit 7, and then we can carry on what we are doing. So to set up these things, we have different ways of doing it. So for example, I'm just going to show you some coding examples over here. Show the instructions. To enable the timer 0 overflow interrupt, and timer 2 compare match interrupt, and B disable timer 0 overflow interrupt, and C disable all the interrupts. With a single instruction. So now in A, we have to enable the timer 0 overflow interrupt and timer 2 compare match interrupt. So in timer unit, we have got the register TIMSK. So inside of that, we have got 7 down to 0. I don't know if I can fit everything over here. We have got T0 IE. It's not gonna happen. Let's start from this side. OCIE2 TOIE2 TICIE1 OCIE1A. I don't think I can fit everything over there. Okay, let's do something else. Let's keep it this way. So this is TIMSK 7 down to 0, and bit 0 is timer overflow interrupt enable 0. Bit 1 is timer 0 output compare interrupt enable. Bit 2 is timer 1 overflow interrupt enable. Bit 3 is output compare interrupt enable 1B. Bit 4 is output compare interrupt enable 1A. Bit 5 is timer input capture interrupt enable 1, and bit 6 timer overflow interrupt enable 2, and bit 7 is output compare interrupt enable timer 2. So this is TIMSK, and if you want to set these things up, we just need to set them to 1. Now let's go back. It says enable the timer 0 overflow and timer 2 compare. So timer 0 overflow and timer 2 compare match. So as I said, the art of embedded engineering is to know which register to set and what the values are we going to set. In this case, we are going to set the register TIMSK and the bits timer 0 overflow and timer 2 compare match. So let's move to the next one. That means timer 0 overflow is this one, bit 0, and output compare to for timer 2 is that one. So that means that has to be 1 and that has to be 1. So this is actually bit 7 and bit 0. You can actually say that this is 0 hex 1 0 0 0, or let's say sorry, let's write in binary first. So 1 0 0 0 0 0 0 1, which is giving us 8 and giving us 1. So 0 hex 8 1 is actually the value that we need to set for TIMSK. Okay, now what we can say about this, we can say LDI R20. This is a one way of doing this. 1 to be set of TOIE 0, so that's actually specifying bit 0, and 1 for, I'm just gonna write it as the next line, but it has to be next to it. 1 for the OCI IE2. Okay, so this is actually saying us that TOIE0 and OCIE2 are going to be 1. And then you can just say out the register TIMSK R20. So this is actually setting those timer 0 overflow and timer 2 compare match to be 1 and ready for interrupt, and of course global interrupt enable we need to add over there. So this is part A of that question. In part B, before we move on, let's check part B, what is asking for. Disable the timer 0 overflow interrupt. So if you want to disable it, we have to use the other way around, actually, the code. So I'm just gonna rewrite A first. Oops. So A was LDI R20 1 TOIE 0 and 1 OCIE 2, and then out TIMSK R20 and global interrupt enable. Now in B, we have to disable the timer 0 overflow interrupt. So to disable it, we just need to get the register values first. So I'm just using in command over there, and I store the values into R20 because I have to clear the flag or disable the timer 0. Then what I can do, I can just use a masking of R20 with the value hex FF with the inverse of the bit that we are setting. So this is actually selling that. I'm just going to write a comment over here. TOIE0 is going to be 0. And then out TIMSK R20. Okay? Or what we can do as an alternative, we can say in R20 TIMSK, then we can use clear bit in register R20, and we can just say TOIE0, whatever is easy for you. This is actually doing the same function. Okay, it's the same thing. And we can just say out TIMSK R20. So that was part B, and part C it is asking for disable all the interrupts with a single instruction. Disable all the interrupts with a single instruction means by just using CLI, we are actually clearing interrupt bit on D7 of status register. Okay, so this is what we can do. For here, I'm just gonna show you the alternative of it. Over here that we have used these instructions, we can actually use something else. We can actually say LDI R20 0 hex 81. So this is coming from which we already observed over here, 0 hex 81. So we can just directly use that to set those two together. Okay, so this is how we are using the registers and how we are setting them up for allowing interrupt event to occur. Right, the next thing that we are going to cover is a simple example that we need to concentrate on to see how we can set up and use a interrupt service routine. So it says use timer 0 to toggle pin port B5 in 4 microseconds. While at the same time data is being transferred from port C to port D, and we have got the crystal frequency of 8 megahertz. So we have to use the timer 0 to toggle pin port B5 in 4 microseconds, while at the same time data is being transferred from port C to port D. Now, port C to port D transfer has to occur all the time. So it just gets the value from C and transfer to D. C to D. Switch is on, put the LED on. Switch is off, turn the LED off. Okay, this is going to be in the main program. But we need to have a timer 0 interrupt whenever it reaches to 4 microsecond. It has to toggle port B pin 5. So some of the necessary steps for this operation are as follow. As we are going to use timer 0, we need the TIMSK register, which we are going to set timer 0 overflow bit. Okay, and on the other hand, we need to take care of the timer register, the control register, because we have to do some operations. So it's going to be an overflow, so this is a normal mode operation without any pre-scaling or anything. So this has to be set with TCCR 0. And of course, we need to know the value for TCNT, which is the timer register value for 4 microseconds. Now, the first thing first, we have to do the calculation. So we have got 8 megahertz clock. That means 1 over 8 times 10 to the power 6 will give us the period of that, which is 1.25 microseconds. So that's our period. And we need 4 microseconds. So 4 times 10 to the power minus 6 divided by 1.25 times 10 to the power minus 6. So we are going to get just a second. 1 over 8 as well as 6. Sorry, that's not the right one. No. That has to be nanoseconds, not microseconds. 125 power 10 to the power minus 9. So over here, I'll just change that to 125 times 10 to the power minus 9. So this is actually going to give us 10 to the power minus 6 divided by 125 10 to the power minus 9. It's going to give us 32. So we need 32 cycles over there. And we can easily use that value to set for the timer. So I'll just keep that one over there. Next thing that we need to do, we have to specify what is happening when the reset is coming in. So for the reset, that means we need to start with .org 0, and we have to say that, let's keep this color, I think it's visible, okay, and we have to say that jump main. So we are allocating that space for interrupt vector table. Then we have to decide, or we have to find out which interrupt vector location we are going to use for timer 0. So we have to look at the interrupt vector table. Maybe I can go back to find out. Okay, so interrupt vector table, we need timer 0 overflow. So timer 0 overflow, it's somewhere here, which is 0020. So let's just say .org 0 hex 20 for interrupt service routine. So over here we need to jump when we are in that vector to timer 0 overflow ISR. I'm just giving a name. You can put any name over there. So let's go back to our question. Okay, now we have got where we have got the reset, the vector table, and the ISR for timer 0. Then we need to start with again .org for the main. It can be somewhere above the vector table. I'm just gonna put 100 over there again, and over here I'll start to my main. Now, as we are using interrupt service routines, we need to use stack. So for the stack, I'm just gonna do init stack, assuming that I'm using a macro which is already defined. So R20 high ramend SPH R20, R20 low ramend SPH SPL R20. So this is going to set the stack for me. Then the next thing that we are going to do, configure pins to be utilized for inputs and the outputs. So port B is going to be toggling, so that means port B pin 5 is going to be an output. So I can say over here SPI DD RB 5. So we have got an output. Out. Then we have to set port C to be an input. So LDI, we didn't specify which pin, so we're just going to use LDI R20 0 and then out DDRC R20. And we have to do the same thing for port D. It's going to be R20 output, so out DDR DR20. Now we have initialized our ports and everything for inputs and outputs. The next thing that we need to do, set up timer 0 overflow interrupt, then set up global interrupt enable. So as we already seen, for the TIMSK, timer 0 overflow flag is at bit 0, so I just need to set that flag. So all I can do over here, just say LDI R20, a little bit down, LDI R20 1 for bit 0. And then we have to out this to timsk from R20, and of course we have to set the global interrupt. So now we have got the third part or the fourth part. We set it up, the interrupt that we are going to get for timer 0 overflow. Then we need to set the timer because it has to count. So LDI R20, the register value that we need to put in for counting for 4 microseconds. So for 4 microseconds, that means we need 224 machine cycles. So 256. So 224 minus 256 is like minus 32 that we need to put in for 4 microseconds. Then we have to out that onto TCNT0 timer 0s. So that's going to be R20. Then we need to do that again with R20 0 hex. What will be the value for TCCR0? So TCCR0, we need to have the register for the values that we need to have. So it's going to be, these are all going to be 0 because we are not going to change to mode. It's going to be a normal mode, and without pre-scaling is 0, 0, 1. So that means we just need to set this to 0, 1. You can check that out from the timer course or from the data sheet, and that's going to be TCCR 0 R20. So now we have got the timer part, set it up in the normal mode with the value to count up to 4 microseconds. And what we are going to do in the main program, we have said that we want to transfer the value of port C to port D. So here continuously we are going to say that R20 will have, instruction in R20 is going to be our pin C. So we are getting the pin C value into R20, and then out onto port D the value of the pin C, and jump here, it's going to wait over there all the time. So it's just going to do that a couple of times. So I think we have lost the connection. Just a second. I'm just waiting, sorry. We have lost the Wi-Fi connection at the moment. I'm waiting for it to reconnect. So while we are waiting, what we have done so far is we determine what is going to happen after the reset. So that's why we put the jump on, or a jump instruction on instruction to program counters at the program memory 0, so that we can jump directly to 100 for the main, and we place the ISR service for the timer 0, which is hex 20 for interrupt vector table, and that's done. Then we initialize the main program to be at 100, and we initialize the stack that we are going to use for a interrupt service routine. Then we have configured the pins for inputs and the outputs. So port B is going to be port B pin 5 is going to be an output, port C is going to be an input, and port D is going to be an output. So we have done that as well. Then we then set up the timer 0 overflow interrupt and the time global interrupt enable, and that's also done. And then we initialize the timer for 4 microsecond count with the normal mode, and we enable the counting. Then what we have done, we copied the port C value into port D forever. And the next thing that we are going to do is ISR for timer 0, which whenever it overflows, it has to toggle the port B pin 5. Okay. So we lost the connection. Now we are back and we can carry on. So if that fits in, we'll carry on. I think we are ready. Yes. Now the thing is, the ISR service, it's going to just toggle port B, because as we already set the timer over here, so we set the timer over here and the overflow flag, we just need to wait for the interrupt to occur. Actually we don't need to wait because the program is running, it's sending inputs to the outputs. Whenever the 4 microseconds is filled out over here, so we have an overflow, we will just jump to the timer 0, overflow ISR. So over here, what will happen? We just need to get the port B, whatever it has got the value. Then we have to toggle that port B, so we can just use XOR R16, R17 and out port B R16. And most importantly, when we are done with the subroutine, we just need to do, I'm just gonna write that over here, ret I. So return from the interrupt back to the original routine over here. And whenever we have got back to the original routine, we have just reset the interrupt enable for global interrupts and wait for the next interrupt to occur. Okay, so this is how we can derive step by step what is actually needed from us and how are we going to set the registers one by one. And you can see the code over here as well. It's the same thing that we have written down. Only thing that I avoided, I use init stack macro rather than defining this again. So, but you have to define that macro somewhere. The important parts, so we jump the main, so we are allocating the interrupt vector to be from address 0. Then hex 20 is giving us the interrupt vector for ISR timer 0. Then we do the main, and then we initialize the interrupt for timer 0 overflow and the global interrupt enable, and then we initialize the timer to count up to 4 microseconds within the normal mode. Then we send input to the output. This is the ordinary function of the microcontroller is asked for, and whenever the interrupt service routine is running, interrupt occurs, we just toggle the port B. So the next thing is timer 0 compare match. So the first example, this one was timer overflow interrupt. Then the timer 0 compare match, we just have 40 microseconds and then we toggle. And we have got 1 megahertz clock over here. So that means it's the similar idea of what we have done, like initializing the stack ISR at the correct flash location. So we have to find out the ISR, the interrupt vector, related with the CTC mode, the compare match for timer 0. So if I go back, timer 0 compare match is in 1E, as you can see. Okay, so we have to use that 1E location for compare match instruction. So if we go back to our question, so that is going to be set to 0 hex 1E for output compare for timer 0. Then we have to initialize the timer. So the timer has to count up to 40. As we have got OCR 0 value to be set in, it has to count from 0 to, with the 1 megahertz clock, 0 to 39. So that means OCR 0 value should be 39. And we have to set the TCCR over here to be in the compare mode or CTC mode. So we have to set this mode to be 1, and that has to be 1, so it's going to be 0001001, which is 9 in this case. So we have got 39 for OCR and 9 for TCCR, and then we have to enable the interrupt. So to output compare, we need to enable the first bit of the timer, not bit 0. Bit 1 has to be enabled. So we can just specify OCIE 0, or we can just say 0 hex 02. So as you can see, 39 9 is set for timer, and then OCIE 0 has to be set, and we enable the global interrupts. That's the only difference over there, and the rest is exactly the same. Okay, and I think this is pretty straightforward, and it's clear of what we are actually doing. Now the next thing, so we have said that at the beginning of this lecture, the interrupts has got their own priorities. So how are we going to define these priorities? We don't need to define them actually. This is actually done by the AVR itself. So with AVR, what we are actually having over here, with the interrupt table or the vector table, they have organized when they are designed in a way that the highest priority will get the lowest address, and the lowest priority will get the highest address. So you can see from the arrow over here, highest priority, so external events has got the highest priority compared to internal events, or the timer has got highest priority compared to SPI or USART, okay, or ADC. So this is the priority order. Highest priority is the reset, then the external interrupts, then the timers, SPI, USART, ADC, EEPROM, and the timer, extended timer 1 to 3, and USART, and so on. Okay, so highest priority gets the lowest address. Another question that we have set, or the important part that we have set, interrupt, can it be run inside of an interrupt? This is actually possible. So while the interrupt service routine is running, you can actually interrupt the CPU for any some other events. So the I flag is cleared when the AVR begins to execute the ISR. So status registers I flag bit 7 is going to be cleared. So interrupts are disabled. And we have said that in ISR, when the red I instruction executed, it will be reset. Okay? However, with the nested interrupts, what we can do, we can actually set an additional interrupt by enabling the I flag while serving an interrupt. So as this is disabled, we can actually re-enable it and we can wait for another interrupt. But we have to be really careful. So we have to be careful for the priority by which the nested interrupts will be served. So based on this. And we have to be careful the correct stack use. So if you are pushing or popping register values onto the stack, we have to be careful with the another interrupt that we are calling, that they are not using the same registers or they are pushed in or popped out at the same amount. So the state of the previous interrupt trigger. So for example, if an external pin active low interrupt triggered execution of ISR, enabling interrupts within the ISR too early may cause the same ISR to be re-entered infinitely. So we are actually having stack overflow problem over there. So we need to be really careful if you want to call interrupt in an interrupt. So I'm just going to show you an example of a program. It's asking for, does the following program work? So what is happening? Okay, we have got timer 0 compare match vector initialized over here. Then we have the stack. Then R20 is used to set up the ports, and then OCR is set to 160, and timer counter register is set to 9. So we are doing in CTC mode. Then interrupt is enabled for output capture or compare for 0, and that's enabled. Global interrupt enabled. Then we are setting the ports for C to be an output and D to be an output, and then we are sending R20 values by incrementing R20 and sending out from port C. Now, then whenever the interrupt comes in, we jump to the interrupt service routine, which is using R20 again in pin D, and it's increment R20 in service routine. Now, what is important over here, as we are changing the value of R20 over here, and we are changing the value of R20 over there as well with increment, and that's also incrementing. This is actually going to be a conflict over there. So both of them, the main program and the service routine, are using R20. When we get out from the service routine, R20 value will be whatever we have got over here, not whatever we have got over there. Okay, so this is going to create a conflict, and it will be corrupted based on the interrupt. So there are two things that we can do to avoid this to be happening. The first thing is, this can be R21, this can be R20, so we can actually say that we can use a different registers for different tasks rather than using the same one. But if you have a larger programs and you have a limited number of registers that you need to use R20 there, you don't have any other choice, we can actually do the context saving, which I already mentioned. Context saving is actually, as we are doing push and pop on the stack, we can actually pop the value of R20 over here into the stack. Then while we are running the ISR, we can use R20, and then we can pop out the value from the stack back into the R20 and then return back to original routine. That means we don't lose the value over here. And this is known as context saving. Okay? So with the context saving, we can push R20 in ISR onto the stack. We hold it over there. We perform the routine. Then before we get out from the routine, we pop back the value of the R20 in, which we have it over here, and then return it. So we can save the context of R20 register, and we don't lose the value of it. So this is how we can use interrupts and the registers together. Again, if you have any question related with this, note it down and ask me during the QA session. So the next thing, or the last things that we are going to consider in this chapter is, up until now we have seen how we can use assembly language to do this type of stuff, but we are going to see how we can do the same things with the C programming language. So it's pretty similar. Whatever we have to do for assembly, we just repeat the same thing for the C as well, setting up the register, the values that we need. And the only thing that you don't need to care about is the vectors that we are using. These are already defined with the AVR C libraries, and you don't need to specify the vector for that ISR. So over here is an example that we have done for 4 microseconds. So on the right you can see the assembly language of it, and on the left you can see the C language of it. So DDRB pin 5 is an output that is already set. TCNT has to be -32, which is set over here as well. Then TCCR is going to be 1, so TCCR is set. Then TIMSK, so interrupt enable for timer overflow, it's going to be set, so that's done. Then SREG, status register bit 1 for global interrupt, SEI can be set using this. Then DDRC is going to be an input, and DDRD is going to be an output. So these are all set it up, and we are just doing input to output continuously. And whenever the interrupt comes in, so whenever 4 microseconds is filled out, it will directly jump to the interrupt service routine. So it's a ISR timer 0 overflow vector. So these are all defined in the compiler, so you don't need to worry about that. And over here TCNT is going to be the values or the overflow, so we reset it, and then we just toggle port B. So that's what actually you need to do, and you don't need to do anything else over there. It looks pretty straightforward compared to the assembly, because you have to do LDI out over here, but over here you don't need to do that. So, but I suggest you to learn how we can set these things up in assembly as well. And normally, as you can see, the compilers deal with the ISR vectors. On this one, you can see that you can reach a symbolic interrupt name list for interrupt vectors. So you can use a IVT, interrupt vectors, and you can find out the names for each of these interrupts, and you can use those directly. Okay, so you have the list and you can just use them directly. So the next example is showing that use timer 1 and CTC mode to write a program that toggles pin port B5 every second, while at the same time transferring data from port C to port D. So it's pretty similar to what we have done over here. Rather than using timer 0, we have to use timer 1, and we have got to do that every second. Toggle port B, and we have got 8 megahertz clock. So 8 megahertz clock for the prescaler. We have got 7812, and for the OCR, which is going to be in CTC mode, that's going to be 7811. And so we have to use that value for OCR. So whenever we reach there, it will just fire the interrupt, and we will do the toggling on interrupt pins. So TCCR1A, TCCR1B can be configured based on this configuration. And we are doing prescaling because of we need to have a second over there for 8 megahertz. So that's why we are doing prescaling, if you are wondering why. And based on that, we set this up. So TCCR1A, they're all going to be zeros because we are not going to set anything on there. But on TCCR1B, VGMs has to be set for CTC. Okay, so that should be 1. And then we have got CS12, CS11, and CS10. So from there we need to set that to 101. Okay, let me note this down. I think it will be better to follow, easy to follow. So our OCR1A is going to be 7811. Okay, and this is actually 0 hex 1 E83. On the other hand, TCCR 1A is going to be 0 hex 00. We don't need to set anything from there. And TCCR 1B is going to be, so VGM 1, 2 has to be set. So bit 7 is 0. Bit 7 is 0, bit 6 is 0, bit 5 is 0, bit 4 is 1. So 0, 0, 1. Sorry, bit 1, 2 is 1. So this is all 0. So the first part is 0. Then this is going to be 1. And for the prescaler, it's going to be 1, 0, 1. So it's actually going to be 1, 1, 0, 1, which is equivalent to A, B, C, D over there. And that's for TCCR1B. We have to set it up. Then we need to have TIMSK. So we are using timer 1 in CTC mode. So if we look at the register, where is the register? TIMSK. Okay, TIMSK timer 1 CTC mode is that one. So OCAE1A. So that's going to be 1 OC interrupt enable 1A. So that's set for TIMSK. And of course we need to set status register global interrupt bit to be 1, and DDRC is going to be input, and DDRD is going to be and output. So while we are doing that, we have to wait for interrupt to be happening, and then we can toggle it. So again, the art of embedded systems, we have to know what to set and how to set. So that's what we are doing, which registers and the bits that we need to set. So once we have done that, writing a code for it should be really easy, because that's what is going over there. So TCCR1A is 0, TCCR1B is 0D, 1A high byte is 1E, that part, and low byte is A3, so that's that part. Enable output in CTC mode for the timer 1A, and the global interrupt is enabled. So port C is going to be an input, port D is going to be an output. Transfer the value from pin C to port D, so it's just getting whatever the values, and whenever the service routine comes in, it just toggles pin 5. And one more example. Assume that the int 0 pin, which is an external interrupt pin, is connected to a switch that is normally high. Write a program that toggles port C whenever int 0 pin goes low. Use the external interrupt in level triggered mode. So what we need to consider, we have to consider external interrupt mask register, and we have to consider the EISCR. So we need to have the low level, so ISCN1 and ISCN0 has to be set it up. Now EIMSK is going to be what? So interrupt 0 is bit 0, so that has to be 0 hex 01, or we can just say 1 for int 0, and E1 EI interrupt enable CRA is going to be 00, because we just want low level, so we don't want to set anything else over there. So that's going to be 0 hex 00. This is default. And all we need to do, DDRC pin 3 is going to be 1. Then port D pin 1, 2 is pull up activated. Then EIMSK is going to be 1 for interrupt 0 pin, and then for EICR1 we can just say EICRA equals 0 hex 00, but as this is the default value, you don't need to set this up at all if you're not going to change the value of it. And then we have got sreg ibit is going to be 1, global interrupt enable, and we have to wait there forever, and whenever the interrupt comes in, we just need to toggle that pin. So you can see the code is pretty straightforward once you know what you are setting up. So this is more important. Then you can put everything down and you can just toggle port C. So this is the end of chapter 10, which we talked about interrupts. We talked about the polling versus interrupt. What is interrupt? How we can use interrupts with the interrupt vector tables. How we need to set up the code, the registers that are necessary if based on the interrupt source, external or internal. Then we have seen different examples in assembly how interrupt is executed on CPU with the program counter and the stack to be used together, and we have seen that we need to enable the interrupt with the SREG bit 7. Then we have seen the context saving, so if you are using the same registers and we don't have any other chance, we can do context saving, so we can push the value of R20 into the stack, and then once we have run, we go through the interrupt service routine, we can pop it back out and we use the same value for that register. And we have seen different examples for C programming, which is pretty straightforward once you know how to set up these registers. So I hope everything is clear, and if you have any questions or confusions, do not hesitate to contact me, or during the office hours or the question and answer sessions you can ask me over there.